Welcome to Analog Electronic Circuits. Today is lecture 15 and we are going to continue what we were discussing in the earlier class, and we were working on current mirrors and then current sources. We were trying to work out some reference current sources, and then we are going to look at a few applications of current mirrors and current sources in terms of biasing circuits. Okay. So, in the last class we were looking at a particular circuit. We were trying to make a current source as opposed to just a current mirror, because mirrors we know, we understand, but what is a current source? How do I actually make that initial reference current? And the way we were doing it, first we said let us just have one PMOS current mirror and an NMOS current mirror, but that did not quite work out because it could have conducted any amount of current. Okay. Next, what we did was we had a PMOS current mirror and we changed the ratio on that. The NMOS current mirror, we had a ratio of 1:1, in which case we found that no current goes through, and then we were working out a third one where in one case I have a PMOS current mirror, I am sorry, this is what I had. So, the NMOS side is not really a current mirror per se, right. It is not really a current mirror, but on the PMOS side I had 1:4. Okay. So, what that means is that if this current is I, then this current is 4I, because it is a PMOS current mirror with 1:4 ratio. Now, when I goes through an NMOS, this is of ratio 1:1, the NMOSs are of ratio 1:1. Let us say when I goes through an NMOS, let us say it creates a voltage VGST, VGST plus VT of VGS is required. When 4I goes through, it is going to create 2 VGST plus the same VT, because I is proportional to VGST squared. So, the voltage here is 2 VGST plus VT. The voltage here for this particular NMOS, it requires only VGST plus VT. So, this much is VGST plus VT, which means that this voltage is just VGST. But if this has value of R, then that means that I times R is VGST. But VGST is nothing but square root of I by K. All right, and then you can cancel out the i's. So, root I is equal to 1 by R root K, in which case I is going to become equal to 1 by K R squared. Okay. Now, just quickly check the units. K has units of Siemens per volt. So, ampere per volt per volt. R has units of V by I. So, volt squared per ampere squared. So, net result is ampere in the denominator, 1 by ampere in the denominator, which means that in the numerator you get amperes. So, the dimensions are correct. Okay. The entire this expression, the dimensions are correct. So, we are probably on the right track, we are on the right track. Okay. So, you understand this logic, how I got the value of I, and I is not 0 over here. I could have been 0, 0 is a solution. When I cancelled out root I from both sides, I could have been 0. Okay, but we have another solution, a non-zero solution, which happens to be I equal to 1 by k times r squared. Okay. What use is this? So, if I set up something like this, then I will get a current over here, where which is equal to 1 by k times r squared. Now, on the face of it, it does not seem very useful, but if you think about it, there is one more thing. What is the GM of this particular device, or any device which carries a current I? So, ID is k times VGS minus VT the whole squared, right. GM is dou ID by dou VGS. Right, this is something that you know, and you can write GM as 2 k times VGST. That is one way of writing it, it is a direct derivative, but then you could also replace k with I and VGS. You could also replace VGS with I and k. So, this particular expression GM is equal to 2 times k times VGST. This is when the knowns are k and VGST and I is not really known. Of course, you can compute I from k and VGST, but if you fix I, then maybe it might be easier to do it in a different way. Okay. So, for example, you could replace VGST over here with VGST squared is equal to I by k. All right. So, this is another expression for GM. GM is 2 times square root of k times I, and in this case VGST has been taken out. All right. Now, in our setup, in this setup over here, right, I have I and k and no idea of what VGST is. All right. I know that I is equal to 1 by k r squared. So, maybe you should use something similar. All right. In fact, you already see that k times I, you pull this up. So, k times I is 1 by r squared, or in other words 2 root k I is 2 by r. All right. So, what is going on over here? So, what I am saying is that this particular device is carrying a current I. Okay. The GM of this device is 2 by R. The GM of this device, this particular device is carrying a current of 4 times I. Okay, where I happens to be 1 by k r squared. So, what is its GM going to be? So, the GM of the device is 2 times root k I. Okay. I over here is 4 times what it was in this case, in the earlier case. So, let us look at it. So, if I have a device which is size W by L and it is conducting a current I, okay, then its GM where I is equal to, this means that this particular device will have a GM of 2 by R. All right. If I have another device which is conducting 4 times I, what is its GM going to be? This is the current that it is conducting. So, this I is not the same as this I. So, ID in this case is 4 by k r squared, right, and therefore, GM is going to be equal to 2 square root of k times ID, and ID is 4 times k 4 by k r squared, k and k cancel out. So, you will have 2 by r times 2. So, GM will be 4 by r in this case. Okay. So, the GM of this particular device happens to be 4 by r, where r is this resistor. Now, what I am going to do is I am going to tap out this voltage and mirror it with another device. Okay. If I keep the W by L same, then this current will also be 4 I. Okay. If this is W by L and if this new device also has a ratio of W by L, then this current will also be 4 I, and therefore, its GM is also going to be equal to 4 by R. However, if I make it 10 times the size, W by L is equal to 10, then what is its GM going to be equal to? Its K has gone up 10 times. ID will also go up 10 times. So, now this is going to conduct 40 I. Okay. So, just look at it. So, this is 40 by k r squared, but k is 10 times, this k is the original k and the k of this device is 10 times larger. So, in this case GM will be equal to 2 times root over 10 k times 10 times 4 by k r squared, okay, and you will get 40 by r. Is this okay? So, you will have a base GM, this is going to be your base GM. So, if I have another device mirrored out from this particular voltage, it will have a GM of 4 by R. If I take a 10 times larger device, I will get a GM 10 times larger. If I take an n times larger device, then its GM is going to be n times larger. In other words, what I have done is as follows. I have made a circuit that looks like this. So, what are these 1 and 4? They are the W by L ratios. And then I tap this voltage out, okay, and the claim is that this current, this is a current mirror, 1 is to n current mirror. This mirrored current is such that the GM of this device is equal to n times 4 by R, where R is the value of this resistor. So, this I is such that the GM of this device is n times 4 by R. Okay. So, this is a way to fix the GM of individual components in the circuit. For example, if I now pull this current through another MOSFET, okay, suppose I draw this current through another MOSFET and that MOSFET has W by L equal to 1, or let us say that MOSFET also has W by N equal to N. Okay. In that case, the GM of this particular MOSFET is also going to be N times 4 by R. Is this okay? So, I can fix the GMs of all the different components in my circuit just by adjusting the value of R. So, I fix the value of R, immediately I know what are the values of GM in the rest of my circuit. Okay. So, this is a very useful circuit, this is used all the time, this kind of a circuit is used all the time. This is called a constant GM biasing circuit. Okay. What is the utility of this? The utility is that whatever the temperature might be, whatever Vt might be, see Vt is not even popping up in the expression. It does not matter what is the value of Vt, it does not matter what the temperature is, it does not matter what else is going on in the circuit. Just by virtue of these ratios and the value of one resistor, you can fix the transconductances of all the other elements inside your circuit, and this happens to be something very useful. Okay. So, let us see how. I mean, how do you bias a circuit using current sources and current mirrors, right. So, for example, in our last a few sessions back, we were working on a cascode amplifier, remember. So, the cascode amplifier looked like this, and we said that we will just put resistor 1, 2, 3, 4, 5 and create the bias voltages. Okay. But let us not do that. Instead, how about I try to bias with a current mirror? Is it possible? And the answer happens to be yes, it is possible. Okay. All you have to now do is work out something like this. So, this would be a Wilson current mirror. You could use Wilson, you could use anything else also. Okay, let me redraw. I have made a mistake over here. Let me redraw. So, this was the main branch of the circuit, and we have to fix the voltages at the gates of these 4 transistors. This was the object, this is the objective. The way I am going to do it is I am going to use a reference current source. What is this reference current source? This reference current source could be something like this transistor over here. Okay. I have got a constant GM biasing circuit and then the mirror coming out of that. So, that could be this reference current source potentially, okay. It could be something else. All right. Now, these two voltages will be just right such that this bias current is the reference current. Is this okay? There is a Wilson current mirror. The impedance looking up from this node is just what it should be. Fine. All right. Now, we go a next step further and we create another copy of this current. So, this is now a copy of a copy, right. It is just another copy of the same reference current. So, this is also the reference current. Now, what I am going to do is I am going to create the bias voltages for the NMOS devices. And again I am going to do a Wilson current mirror. Okay. So, now this current is mirrored over here. So, the red current and the green current are going to be exactly the same. All right, is this okay? So, all the elements over here are parts of current mirror. So, one reference current mirror that creates this current, another mirror and another mirror. Okay, if you want you can draw the MOSFETs the other way round. Okay, if you do not like my drawing, you can draw it backwards with the gate on the right side. Okay. And then where is the input to this amplifier? There was supposed to be, this was supposed to be an amplifier, remember? Okay. So, the input has to be coupled, AC coupled, all right, and the upper stages have to be common gate, otherwise I mean the upper stages, if the gate over here also vibrates, then that is not a good idea. So, the upper stage has to be common gated to ground. The voltage here also has to be small signal ground. And this has to be isolated out, okay, so that this current mirror side does not vibrate at all, right. This is, you can place a large, very large resistance over here, such that this current mirror side does not change with the signal at all, okay, and at the same time you have to AC couple it to ground. Is this okay? And then the output is from here. This is understood or not? So, I started with a reference current, mirror, mirror, this is the bias, okay. Mirror's mirror is coming here, right. So, whatever is the reference current, this side is also, it is the same reference current, right, because this has been mirrored, copied and then another copied twice. Okay. And then I need to isolate the bias circuit from the signal circuit. All right. So, I have isolated the bias circuit from the signal circuit. This bias circuit, this should not become, this network should not become part of the small signal circuit. okay, it has nothing to do with it. So, therefore, I have isolated, I have disconnected it with a very large resistor, right. This resistor is not conducting any current for DC, therefore, it is going to behave like a short circuit for DC, but for signal there is a large capacitor here which makes it a short circuit. So, this resistor will be allowed to conduct current, will need to conduct current as required, right. So, these are not a short circuit for AC, but it is a short for AC, it is an open because it is a very large resistor for AC, and this is a short for AC. Likewise, I needed common gate over here, so short for AC. These points also need to be shorted to ground. Okay. So, all the gates they do not move, fine. This is basically the idea behind this circuit. So, you have all these coupling and decoupling capacitors, and you need to isolate the bias from the signal. Fine, this is the cascode amplifier, and this is biased using current mirrors. All right. Now, if I say that this Iref is such that when Iref goes through a MOSFET with W by L of 1, then the GM of this MOSFET is 4 by R, then that means that the GM of, so Iref has indeed been mirrored. So, that means the GM of this MOSFET is fixed in advance. So, the overall transconductance of the circuit when I do the short circuit current experiment is GM approximately, and that is fixed in advance from outside with the help of that R. Now, that is something very neat when you can control parameters inside the circuit using some element outside, right. I tweak the value of the R, I immediately know that the short circuit transconductance of the circuit is going to be so much. That is something very neat. Okay. So, this is as far as biasing techniques go. There is also an insight as to how you can use current biasing to make your cascode amplifier. Now, after this we are going to move on to a new topic, and this new topic is the topic of differential amplifiers. Okay. And it is like this, that whatever you learnt in the first few classes, the common gate, the common source, the common drain circuit, over there we used one bias circuit, you know, R1, R2, RD, RS, that kind of a bias circuit. Now, it so happens that that technique of setting the operating point of the MOSFET is not very nice. Okay. It does not allow you to, for example, control the GM of the MOSFET, whereas a technique such as this allows you to control the GM of the MOSFET, right. The GM of this MOSFET is well known with the help of an R from outside. That is something very neat. Okay. So, most of modern analog design is with the help of current mirrors. Almost all of modern analog design is with the help of current mirrors, where you bias the MOSFET with a current source as opposed to these voltages. Okay. So, the entire mindset is somewhat different. So, the mindset is that we are not going to use R1, R2 and create a ratio and then say that this is the voltage at the gate. Let the voltage decide itself. We are going to pull a fixed value of current through the MOSFET, decide the current, and that current is going to fix the voltage automatically. Okay. So, the mindset is different. By the way, in that case also we were eventually doing that, right. Eventually when so initially what we did was we had the source grounded, right, that created a VGS, R1, R2 and VGS, that created a bias current. And then we said that it is no good because ID is very sensitive to VGS. But then later on what we did was we placed RS over here and then you had to crank a quadratic equation to figure out what is the current ID. Okay. ID came out of some quadratic, you basically did some loop over here, right, VGS, VGST plus VT, right, R1, R2, this was VDD, VDD times R2 by R1 plus R2 and then this drop was VGST plus VT, right, and this is ID times RS, and that gave you a quadratic because VGST was nothing but VGST is what? VGST is ID by k square root of that, square root of ID by k. So, square root of ID by k plus VT, IDRS and a fixed value. All right. So, this is a quadratic equation in ID and then you crank the quadratic and you work out the value of ID. Then in the next step we said that it is very hard cranking a quadratic every time. Okay. We are going to make a guess. The guess is going to be that maybe VGST is 0.2 volts. Okay, maybe VGST is 0.2 volts, maybe not, but you make the guess VGST is 0.2 volts and what happens? You drop it out and find out ID. So, ID now is fixed to VDD into R1 R2 by R1 plus R2, that voltage, right, minus 0.2 as the VGST minus VT, the whole thing divided by RS. So, you have actually fixed ID like this. Then you say, then you work back and say what is VGST for this ID, my initial calculation of ID. You find that oh, it is not 0.2, it is 0.15. Then you correct this equation, make it 0.15. Then again find out what is VGST corresponding to that ID. You find okay, it is not 0.15, it is 0.175. Then correct the equation, plug in 0.175 and then within 2 or 3 iterations you will be all set. All right. So, eventually you are actually fixing ID and ID is pretty much equal to some voltage minus VT by RS. So, eventually ID is some voltage by RS. Okay. So, with the help of RS you are fixing the value of ID. Here with the help of the resistor here you are fixing the value of not ID, GM. So, it is similar in the sense that you are trying to fix ID, but not really, you are fixing GM instead over there. Okay. So, let us get back to the new topic. The new topic is going to be differential amplifiers, and before I start this new topic I am going to do some very basic circuit theory theorem. So, these are two boxes. These boxes have all linear circuit elements, resistors, capacitors, inductors, voltage controlled voltage sources, all linear circuit elements are there inside each of these boxes. just that if one is the network N, then the other is the mirror of the network N. They are otherwise identical. These two boxes are identical, but mirror images of each other. And then there are wires coming out of each of these boxes, which I connect in between. Okay. And there is a ground wire coming out, reference, and there is an input wire for N, and likewise since it is a mirror image, there is another input wire for the mirror image of N. So, this is my setup. A lot of wires in between, there are some ground connections, there is an input, and corresponding to the input there is a mirror image of the input. There could be more inputs also. All right, this is the setup. Now, what we are going to do is we are going to apply a voltage V over here and a voltage V over here, right. I apply voltage V at the input of network N as well as at the input of network image of N. What can you tell me about the wires in between over here? Can you tell me anything about the wires here? Hint, use superposition. No, not voltage. Try to tell me something about the current in the wires there. Can you tell me something about the current? Not forget the voltage. Yeah, the voltage is double, that is the, but you do not know, you have no numerical estimate. What about the current? So, the current is 0, right, because if I apply V and 0 over here, then some current is going this way through this wire, and if I apply V and 0 on this side, then equal and opposite current is coming the other way. Then the net current, when I have V and V, then because of superposition the current here is 0, because it can't figure out which way to go, whether to go from here to there or to come back from there to here, right, both are equal. So, when I apply V and V, we are going to call this a common voltage. Then the outcome of the experiment is that the current in the wires is 0, or in other words, if I have a wire and I know beforehand that the current in the wire is 0, I am allowed to cut the wire with scissors. Do you agree? If I have a wire and I know in advance that this wire does not take any current, then why do I have a wire there? I can jolly well cut the wire. Okay? The potential is established. I know in advance that both sides have equal potential. If they do not have equal potential, then there is going to be current in the wire, right. In any case it is a wire, right, it is establishing equal potential, and then the current is 0 through it. So, therefore, I can cut the wire and KVL, KCL is not going to be violated on the other sides, on the other two sides. So, this is something important. So, if I apply V and V over here, then it is okay for me to cut the wires in between. All right, this is experiment number 1. Now, experiment number 2 that I am going to do is I am going to apply V on one side and minus V on the other side. Now, what can you tell me about the wires over there? So, now I have applied V on this side and the plus side is connected to ground. So, this is minus V, V and minus V are the potentials on the two sides. What can you tell me about these wires in between? Once again use superposition. You do V and 0 and then you do minus V and 0, two experiments. The circuits are linear, no let us forget non-linearity in the circuits. What happens? The voltages in between are 0. Why? Because when I did V and 0, I applied V and 0, I got some voltages in between. If I did minus V and 0, then I got exactly the equal and opposite voltages. So, now my excitation is minus V and this is exactly the same as N, this side is 0. So, the voltage, if this voltage was V1, then now it is going to be minus V1. And then I do the superposition and therefore, the superposition is going to give me 0 volts. All right. So, if I have equal voltages on two sides common, then the current in the wires is 0. If I have opposite voltages on the two sides, then the voltages on the wires is 0, which means that I can short the wires to ground. I am allowed to short them in ground because they are already 0. So, I can start calling them ground. Okay. So, in one case it is okay for me to open the wires, in the other case it is okay for me to short the wires to ground. All right. So, this is my theorem. Okay. This theorem has many more corollaries, right. When you have with non-linear circuit elements, there are going to be many more corollaries, but let us not worry about them right now. Okay. So, for example, odd harmonics, even harmonics, what is going to happen? You can work it out. Okay. If n is not linear, right. If n is not linear, superposition does not quite work out. Okay. So, the way we did it, we used superposition to work it out, but if n is not a linear circuit, then how will you do it? So, there are lot of other steps that you have to go through and then you can work out what is going to happen to the odd harmonics, what is going to happen to the even harmonics and so on and so forth. If I apply equal voltages, common voltages, if I apply opposite voltages and so on. Okay. So, those parts of the theorem we are not interested in. This is something that we are going to use. Okay. So, the theorem is that if I apply V and V, then I am allowed to open the wires in between. If I apply V and minus V, then I am allowed to short the wires to ground. The wires in between can easily be shorted to ground, no change in the analysis. All right. So, with this background, so this is the background. Okay. Let us keep this aside and what I need you to think about a little bit is the problem of interference. And along with interference, I also want you to think about noise. What is noise and what is interference? Okay. So, if people are talking outside this room and you can hear them talking, let us say, are you going to call it noise or interference? This is my question, right. If you look at the dictionary, is noise the same as interference? Are they different words? What is the meaning of the word noise? So, you are over here, right, you are trying to listen to me. I am the signal, my voice is the signal, and outside this room there are others who are talking, right, who are disturbing you. Is that noise or is that interference? That is the question. Or in other words, I have this microphone over here, I am speaking, my voice is going to the microphone, right. Now, other people are speaking outside this room, their voices are also reaching this microphone. As far as this microphone is concerned, my voice is the signal. Is their voice noise or is it interference? So, let us say think of the system from the perspective of this microphone. Okay. My voice is the signal that the microphone needs to capture, that is the signal. Others are speaking outside the room, their voices, what is it in the perspective, from the perspective of the microphone? Are you going to call it noise or are you going to call it interference? The answer is that those outside voices, they are going to be called interference. Not noise, not noise. Okay. They are legitimate speakers, they are trying to communicate between each other, and this microphone just so happens to be in the wrong place at the wrong time. It is just overhearing what they are actually trying to communicate with each other. Think of two telephone wires, right, coupled with each other, right. On one wire, person A is trying to talk to B, his voice he is speaking, right, and that is coupling onto another wire which is on which person C is trying to talk to D. Okay. That is called interference, not noise. It is a legitimate communication, perfectly all right, right. It is not noisy, they are speaking nicely, they are speaking to each other, right. And this microphone happens to be at the wrong place at the wrong time, and it is overhearing what those two are trying to speak to each other. Then what is noise? So, as far as circuits are concerned, we define noise in a very different way. We say that noise has nothing to do with legitimate conversations. Okay. Noise is because of physics, purely because of something random that is happening in the physics. Okay. What for example, not for example, this is what I am talking about. So, if you think of a resistor, is made up of some weakly conducting material. Okay. This conducting material has lots of electrons. So, if I apply a potential across this conducting material, these electrons are going to start moving, start drifting. Okay. So, that is the mechanism of drift. But how does drift work? Drift works by pushing, right. I push, you know that, right. That is how drift works. Drift does not mean that the electron over here zips away to that side. No, that is not what happens. Okay. It is more like a queue where the railway reservation queue, right. You have a long queue of electrons and they all want to go, right. There are these queues of electrons and they all want to go from the minus terminal to the plus terminal. So, they are pushing each other, right. This first one is pushing the next one, right. The next one is pushing the next one and so on and so forth, right, and they are going as a queue, all right. So, as soon as you apply the voltage, immediately the first the last one starts pushing, the first one goes in, right. You start seeing some current. It does not mean that there was only one electron that had to zip across to create the current. No, this electron is, they are not really moving very fast, they are moving quite slowly. The electrons are not moving fast, it is just that they are pushing, and that creates the flow of current. Okay. Now, they are pushing in this direction because of the electric field, but there is also pushing because of heat, right. You know, think of a you know, an office where you have lot of people and it is very hot, and all these guys are just, they are just pushing and shoving each other and trying to come forward in the queue. So, there is a lot of sideways motions as well, right, front and back, sideways, there is a lot of pushing and shoving. So, and that happens with heat, right. So, these electrons are not only pushing because of electric field, they are also pushing and shoving because of temperature. Okay. They are also pushing and shoving because of temperature, or in other words, think of this as a gas full of electrons, right, a cloud of electrons, a gas full of electrons, okay, and they are going to push and shove, right, they are going to bounce off each other, it is a sea of electrons, okay, they are going to bounce off each other, and statistical thermodynamics says that the energy in each degree of freedom is going to be related to the absolute temperature T and K, the Boltzmann's constant. So, K T is the energy with which they are going to bounce with each other in any degree of freedom. So, there are 3 degrees of freedom. If you think there are 3 degrees of freedom, then 3 K T. If there are 6 degrees of freedom, then 6 K T, and so on and so forth. Is that okay? So, this is noise. This bouncing off each other, this shoving and pushing, this is going to cause noise, because if I bounce and push and shove, then I might have created an electric field over here, but different values of current might come out. Okay. That is going to be noise, all right. So, there is a very subtle difference between interference and noise. Interference is anything man made, you know, we are legitimate communication going on. Whatever the microphone is picking up is signal plus interference, but inside the microphone there is a resistor, and that resistor is generating noise. Okay. Interference is unwanted, noise is also unwanted, signal is wanted, okay. But interference is something that is man made, it is another legitimate communication. Noise is because of the physics of the microphone. There is a resistor inside the microphone that has some pushing and shoving going on, and that is creating noise, all right. So, it is a very subtle difference, you need to understand this, because why I am talking about it is because with the help of differential amplifiers, we will be able to get rid of interference, but not noise. Okay. Interference we can get rid of it with somewhat to some extent with the help of the techniques that we are going to study very soon. We will not be able to get rid of noise at all, right. Noise is in the physics of the device, right, and that is because of pushing and shoving because of heat, right. If you want to get rid of noise, cool down the whole thing to 0 Kelvin and you are done, right. Let everything there, let there be peace, right, at 0 Kelvin. Okay. So, let us wrap up over here. So, today what we did was we discussed a constant GM biasing circuit, where the current that it generates, creates a reference current, and this reference current is proportional to some 1 by k r squared, okay. And it so happens that if I put this reference current, I draw this reference current through another MOSFET, then the GM of that MOSFET is going to be just inversely proportional to R, and that is it, all right. So, that is something very nice. Now, this reference current can be used to bias any complicated circuit, and we know the GMs of the different transistors in this complicated circuit. So, that is basically the utility. So, as an example, we showed how to bias a cascade amplifier, right, using these current mirrors coming out of a reference current. All right. And then we studied a theorem, and a very important theorem, where we had a network N, a mirror image of network N, connections in between. We applied two equal voltages. We found that the wires in between can be cut, and then we applied two opposite voltages, and we found that the wires in between can be shorted to ground. Okay. So, this is a very important theorem for us, and then we studied interference, the philosophy of interference and noise. So, noise is coming because of physics, interference is everything else. All right. So, let us stop here, and we will continue with differential circuits in the next class. Thank you.